Good morning, everyone, and welcome to this Chemspeed webinar. My name is Chris Dietrich. I'm a Director of Business Development here at Chemspeed, and I'll be your host today. So this is the first in a series of about 5 events, and all of them will be dedicated to the digitalization of R&D and quality control labs. This is a new format for us. And the idea here is to give a voice to our clients and partners. So in the course of the coming weeks and months, they will describe how they make use of our workflow solutions and how that relates to digitalization and what it means for their current and future operations. Today's event is dedicated to a project that is very dear to me and that we carried out for the last 1.5 years together with IBM Research. Our guest is Dr. Teodoro Laino, who led that project at IBM. Teo is a distinguished research scientist in the Department of Cognitive Computing and Industry Solutions at the IBM Research Laboratory in Zurich. Welcome, Teo. It's my pleasure to have you here today.
Hello, Christian. Good morning and good afternoon as well, everybody that is listening at the webcast. Hi.
So, Theo, in a nutshell, you built a machine, to put it in very simple words, that carries out chemical syntheses. But putting this way really doesn't do the project justice, because what we're talking about here is a machine that takes a target molecule as an input and then calculates several possible retrosyntheses, then predicts the detailed protocol for how to carry out those reactions, and then translates all of that into a set of orders for a Chemspeed robot, which eventually executes the process and the corresponding analytics. And I think in one of the interviews that you did recently, you compared that to a pizza bakery, where you basically take a picture of a pizza and then put it into the machine, and the machine will tell you exactly what ingredients you need for it, and then the detailed protocol or recipe to actually make it. And if we translate that into the space of chemistry, it's nothing short of amazing. So to the best of my knowledge, this integration of in silico retrosynthesis and the execution, the automatic execution by a robot is a first. And Theo, you and your team truly pushed the boundaries of what lab automation can do. So during the next half hour or so, Theo will give us an overview of the project before we are going to answer questions about the project and its future. This is a live webinar, and you all have the possibility to ask questions. So if you're wondering about a thing or two that comes up during the presentation, please feel free to type your questions into the Q&A section on the right, and we're going to answer as many as possible at the end. And if we run out of time, don't worry about it. We'll get back to you in any case by email. So before we jump into the presentation, Theo, I was wondering how this project was actually born. I mean, where did the inspiration come from, and when did you decide that this can actually be achieved?
That's a very, very, very interesting question, Christian. I will cover some of these elements in the next 20 to 30 minutes, but to make it short, everything started when here at the lab in Rüschlikon, together with the rest of the group, we have been exploring a novel approach to treat synthetic organic chemistry by treating chemistry as a language. And the performance of the model were so high that the question whether such a mathematical architecture may have driven a chemical synthesis was quite obvious and natural. And that's basically where we started conceiving the entire project structure. So if you allow me, I will just jump directly. So first of all, I would like to welcome again everybody, wherever you are watching the webinar. I will move, as Christian was mentioning, in the next 20 to 30 minutes more into telling you more about the technology. But first and foremost, what I would like to show you, because I believe it's really the best way to explore the entire technology, is to start together in these 50 minutes remaining until the hour a synthesis. So I want to give you first, before jumping into the technical details, some information about how you can use the entire synthesis. I'm sitting now in an office, actually quite far from the lab, and I want to give you an example of something that we can do together in the next minutes. I will go again through the details, but basically, as Christian was shortly saying, the entire project is a project that is heavily machine learning based, AI based. So we have the possibilities to digitalize chemistry, to execute chemical synthesis, mainly in two different approaches. One approach is what we call reading a synthesis from literature. So it's equivalent to do a copy and synthesize, a copy and paste of the synthesis, and then executing it immediately on the robot. So when you connect on the Ericsson platform, and again, feel free to explore these capabilities. You can even freely enable the simulator of the entire Robo Ericsson. You can go for reading from literature. And here, for the sake of time, I was just picking up one patent. I will just look in this patent for the first synthetic paragraph. So let's say a certain compound has been added, first mixed with ethanol, and then a solution was added to a solution of isobutyl bromide and ethanol. Potassium carbonate was added, and the suspension was refluxed at 74, 78 degrees for 5 days. Now, if you just take this paragraph or any other paragraph you find in patents or in articles, and you just go for create synthesis, what is going to happen is that we have one artificial intelligence model, NLP model, that was actually disclosed. The detail of the model were disclosed on Nature Communication middle of July. That is actually interpreting the entire paragraph. Now, in the paragraph was not reported the nature of the compound, so that's why we know that there is a product, but we don't draw the product because the product was not mentioned in the paragraph. And if you look on the inspect, that's exactly the structure of that paragraph. You first make a solution of the 1-bromo-2-methylpropane in ethanol, then you add the solution, you add the other compound, you add ethanol, you add potassium carbonate, and then finally you reflux for basically 5 days. So once you're ready, you can go on confirm, provided you have all the chemicals preloaded in the architecture, confirm, and this will be immediately executed. For today, as we were doing an example a few weeks ago of this exact type of capability, today I want to cover something a little bit different. We want to use the second way of designing a synthesis. So for we are not going to talk about drugs. We are going to talk about materials that are relevant for different type of problems. I will just briefly mention, without entering the detail, while this molecule is interesting, this molecule is part of a fragment of a more complex synthesis of molecules that can be used to capture CO2 from the atmosphere. So this molecule is non-commercial, so we had actually to synthesize it. So let me show you how it works. Again, as I mentioned, the synthesis is more complex, but for the sake of interest, the sake of time, I don't want to keep you here for 6 or 7 hours. You can basically open the workspace, and then you can draw. I'm using the smile representation, but you can draw the molecule. Once you have the molecule drawn, you can go for a new retrosynthesis. Again, for the sake of interest, we will go into an interactive mode. And the very first model is the one that is predicting the possible disconnection that can be used to make this molecule. Now, you see, this one is interesting, but this molecule, again, is not commercial. So let's look for something that contains something that is commercial and actually contains already a solvent. One of the major advantage of Arixen as a platform for retrosynthesis is exactly the one of already predicting ideal solvent. So in this case, we can make this molecule starting from commercial material, THF, which is the solvent, the dimethyldiamine ethylene, and then we have cyanogen bromide. So if we just take this possible disconnection and we apply the disconnection, what it happens is that we have a very precise way how we want to run the synthesis. And then the only thing you need to do, and you can do that one again, even with the simulator of RoboArixen, you can start the robo process. And at this stage, we have another artificial intelligence machine learning model that, given this synthesis, is compiling the exact sequence of operations that is needed in order to make this reaction. Now, let's quickly review together, because these are the recommendations of the machine learning, but you have always the capability to intervene and correct if you believe that something is wrong, or ideally, even for fixing the quantity. So the very first thing is that we are adding the NN-dimethylethyldiamine. Then we are adding the THF, and then we are adding a solution of cyanogen bromide in THF. We add this solution drop-wise. That's a very important part. And then we stir for 1 hour. Finally, you can do a filtration, a concentration, and then a store. Now, this recipe is going to take way too much time. So allow me just to change a few things. I already prepared solution of these reagents to make it quicker. So we will use basically here 1.7 milliliter. This is actually the quantity equivalent for the right stoichiometry. We will add, let's add 15 milliliters of THF. And then instead of making a solution of cyanogen bromide, this would take additional 5 to 10 minutes. Again, we can shortcut, we can remove this operation, and here we can just add cyanogen bromide. We have a solution which is already prepared. We will add 2 milliliters drop-wise, and we want to do that across a time scale of 300 seconds. The reaction of this compound is actually very exothermic, and already the AI model was suggesting us to do the addition drop-wise. Finally, even if the reaction will not be complete, we will wait actually 600 seconds. Let's do even 300 seconds because we are a little bit late. So very likely the reaction will not be entirely complete, but we should see the formation of the product in the mass spectrometry. We don't do any filtration. Again, it's really for interest of time. But in an ideal case, you would do also the filtration, not even the concentration, but we will do just a store. So that's exactly how the AI recipe was recommended. And with a little bit more of time, I would have exactly launched that recipes. But because of the consideration of the time that we have here, I'm just going to cut the corner, confirm, and we see that there are no errors, and then we can just launch it. As soon as you launch it, we are going in a waiting status. You can watch what is happening. Actually, at the moment, we don't have the video stream, but I will be sure that this is recovered in the next 5 minutes. But what is happening at this stage in the waiting status? We have actually the inertization of the reactor. Some of these compounds are water sensitive, and the preparation. This is going to take approximately 3 to 4 minutes, and then we are now in a running status. So this is exactly when the robot is receiving the instruction and is starting to perform all the operation. So I will come back after the presentation. Maybe we will see when we are doing actually the synthesis, the steering, and we are catching some of those actions. One thing that I forgot actually was to add here an analysis operation, but I can recover from another run again and show you what is happening after you place an analysis operation. Now, let me go back to the presentation while the synthesis is running and give you a little bit more of detail. First of all, I would like to, let's say, thank, but also recognize the entire work that I will be describing. Quite often, I will use the first person, but please refer always to the entire team. The entire project has been a very challenging project in terms of integration, in terms of development of technologies. So please refer always to the entire team when I will be presenting some of these things. The very first part is, and is connecting to the question that Christian was asking, is where did it start, the entire concept of ROSEN? It started actually in 2018 when, together with Philip, and at the beginning we were a very small group of people, Philip Schwaller and Théophile Godin, we started exploring the possibility to use natural language processing for treating the synthesis in organic chemistry. The general idea was that if there is a language, and the language is actually characterized by rules, a grammar is nothing more than a set of rules, we should be able to capture those rules with those architectures that are state-of-the-art in terms of learning the structure of a language. So it was very challenging because we didn't really know whether this was working, but the reality is that the very first project that we started working on was the forward reaction prediction. And the forward reaction prediction, if you treat organic chemistry as a language, is easily casted like a translation problem. So you are translating from reactants, reagents into products. And so how did we train the entire model? We collected a large number of chemical reaction. We are talking about more than 2 million in 2018. Now we are above 3 million of examples. And we were training an architecture that is called the neuronal machine translation architecture by exposing a certain number of times during training these 3 million of examples, equivalent to 3 million of sentences, like in Japanese and the corresponding one in English. So that's exactly how you train a translational machine. And this is exactly how we train the initial RxN model. There was a lots of enthusiasm in the community. We made it online at the ACS in Boston in 2018 in August. And very shortly, we reached a very strong community around the software. Today, it's counting more than 15,000 users. And we are already, today morning, we were close to 900,000 prediction made on the IBM cloud. At the end of 2019, we introduced the retrosynthesis. So the forward reaction prediction is predicting products given reactants and reagents. But in a very similar way, you can invert the prediction. So given the product, you can actually predict reactants and reagents. And that's exactly what we did in the example with this heterocycle. So we spent almost 1 year in order to fine-tune the model, and we made the model available in October 2019. I think, the time couldn't have been better. The entire retrosynthetic model has been used by communities during lots of communities during the months of March, April, and May that were looking on designing molecules for fighting COVID-19. And the retrosynthetic model was used as a very effective way to evaluate the synthesizability of the molecules instead of using data models, basically heuristics. In June, we made a semi-official release. Actually, in May, to be completely honest, we made a semi-official release for a first premiere of RoboRxN for a few companies, and then we went a little bit more broader and public on social media in June, and finally a couple of weeks ago we made it the official announcement on the press, where we were running exactly a very similar synthesis on a different type of molecule. Today we are synthesizing something that is useful for CO2 capture. Last time we were synthesizing a molecule, part of a set of molecules that may be relevant for COVID-19. So that's exactly where we are. The last addition to the family of RxN is actually RoboRxN. RoboRxN is building on 4 main parts. The very first part is the extraction of chemical knowledge. And we are not talking only about chemical reaction, we are talking about recipes. One of the concepts that is really fundamentally important is that while it may be easy or relatively affordable for people to do a specific type of retrosynthesis, one of the challenges that we wanted to solve is, given a reaction generated from a retrosynthetic tool, how can we suggest and recommend the optimal sequence of operations? So normally this is a task that takes time, it takes literature review, and it takes a lot of search in order to find whether the reaction was already done, what were the conditions, and we tried really to mimic with machine learning architecture exactly to tackle with machine learning architecture exactly that problem. So we started from more than 9 million recipes that are still relatively small if you consider the large variability in organic chemistry. And sadly enough, we had to go back to roughly 3 million of recipes after an extensive cleanup and purging and elimination of duplicates. So we have now a data set of 3 million, which has a very high statistical value and importance. And we trained all the state-of-the-art models to learn how to cook the ingredients exactly with these 3.5 million chemical recipes. The third part is the integration of AI with cloud. And this is exactly what you experience from your house, from your office. We are talking about an infrastructure which may be easily thousands of kilometers farther from your location, but still you can access the technology, you can use the technology, and you can make science remotely. This thanks to the integration of AI with cloud. And then finally, the one part which is, of course, very important in the entire concept, you can consider that all these machine learning models are doing nothing more than writing a computer program, a general computer program. The computer program can change every time, but we need a processor, we need something that is capable of executing those instructions. And this is where we partner with Chemspeed in order to combine in a very agile and effective way their existing chemical hardware with the entire software stack that we developed using machine learning and cloud. So the fourth part is really the integration of the automation. Now, I want to go a little bit more deeper, few more minutes deeper into these components. The very first part is the AI-driven retrosynthesis. I invite you, anybody of you that has a little bit of interest in retrosynthesizing something, I mean, feel free. It's free. You can access the platform. You can play. We guarantee the privacy of everything you do on the platform. On the other hand, as the entire service is free, I guess it's understandable that we cannot offer industry standards regarding confidentiality. So I always mention, use the tool for toy system. Don't put in the tool confidential data. In case of a data leak, there is no way that we can guarantee the retention of the confidentiality of the data. One thing that is actually very much differentiating our retrosynthesis compared to all the others is that we don't only provide disconnection approaches. As you have seen in the retrosynthesis for this heterocycle, we had already one recommendation about the solvent, and we have been using THF. So that's actually a very important part. Whenever catalysts, whenever solvents are predictable, the retrosynthetic module will predict them. And again, for people that may be less aware, what is a retrosynthesis? This is nothing more than starting from a molecule that I want to design and going backwards compared to the time arrow and identify what are the commercial starting material, the most effective commercial starting material that I can combine together to make the target molecule. As I mentioned before, in order to do that, we are heavily relying on a text-based representation of the molecule. Every time you draw a molecule, the molecule is first converted in a string, and then we are elaborating, doing all these operations with the strings. We are really treating chemistry like a language. And that's exactly where the translation model is fitting. So we have a sequence of atoms describing the product, and we want to generate a sequence of atoms describing the reactants and reagents. And this is nothing more, as I mentioned at the beginning, than a translation process between the language of the products and the language of the reagents. The second component that I already mentioned is the AI-driven actions. So let me give you a little bit more of context, and I can also unofficially let you know that more scientific details on that one should appear hopefully by next week on some of the archive platforms for dissemination of scientific articles. So if you have questions, I'm more than happy to answer any technical question, but I wanted just to give you a glimpse of what is really behind the AI-driven actions. So for every single step, we trained a model that is capable of creating the optimal recipe. This is equivalent, for some of you that may remember, is actually equivalent to Watson Chef, IBM, if I'm not mistaken, in 2012, 2013, made available online one AI model that was generating recipes given ingredients. And we are actually doing the same. Instead of food-related recipes, we are actually working in the synthesis. We managed to train this large number of reaction protocols. And again, one important thing is that this is not about memorizing protocols, but is about capturing patterns. So, for instance, in the entire recipes, there was a filtration process. And the reason why there was a filtration process is because in this reaction, and I hope to have the time to show you after even the vial, in this entire reaction, there is the formation of a precipitate. So the model somehow learned across all the large number of recipes that when you are combining these molecules, there is a salt that is generated, which is insoluble in that solvent, and then is recommending a filtration process. Again, not memorization, but learning of the patterns. And because every single molecule has a specific way of being handled, especially when you combine with the solvents, it's crucially important that these 3.5 million chemical recipes are actually becoming even more in the future in order to cover as much as possible the entire domain of synthetic chemistry. The second part is what I show you at the beginning. You can take a paragraph, and this is, again, another example coming from an article rather than a patent, and you can just do a copy and paste of a synthesis. So you copy the paragraph of the synthesis, you paste it into the tool, and actually you have a natural language processing model that is interpreting the text and giving you the sequence, the coin-size sequence of operations that then can be executed by a robot. The sequence of operation, again, I mentioned at the beginning, but I want to stress it now, it's a computer program. What the machine learning, the artificial intelligence is doing is actually replacing the tedious task of programming chemical hardware. So what we are actually doing is generating computer programs that then can be digested by the hardware and executed on the hardware. It's really the closest thing to a software design, self write-up and then execution on a computing platform. The only difference is that instead of crunching numbers, we are crunching molecules. The third part is, as I said, is the AI-driven automation. So there, as I mentioned, we partnered with Chemspeed for shortcutting the time. We never had an intention to build hardware by ourselves, but we prefer to rely on commercial hardware because this offers guarantees in terms of quality, in terms of reliability, and in terms of specifications. So it's are the very first three components. Whenever you want to embed a system like this one into an operational environment, you have to face with all the reliability issues and also with all the logging issues. If you are transferring 1 milliliter, you won't be sure that you are transferring 1 milliliter and not 1.5. The other thing is exactly the entire concept of consuming the technology. And again, there's a very schematic way for you to understand what we did at the beginning of this seminar. Basically, we were interacting in the cloud. We were drawing the molecules using the AI models in the cloud. Everything is happening in the cloud. And the only thing that remains behind the firewall is actually the automation hardware. And this can be a very effective way also to protect the asset. But all the processing can actually happen in the cloud and is powered by OpenShift. What does that mean? It means that if you want to install the entire structure, software stack on premise or on your private cloud, you can do seamlessly with OpenShift without us changing anything in how the software has been constructed. So this is really going one step beyond in order to allow everybody, independent of what are the confidentiality constraints of the data, to use this technology either on the public cloud, on a private cloud, or on hardware on premise. Everything is available on the RxN website, so feel free to just Google IBM RxN. And as I mentioned during the demo, we have actually a simulator. Of course, you understand it's difficult to give access as of now to everybody. If there are people interested, we are already providing test access. But for all the others, you can experience the entire software stack, all the machine learning model by just enabling the simulator mode. and you will find on the RoboRxN page the activation key. So feel free to activate RoboRxN in your account and play with the machine learning. And if you want to give it a try, hands-on, on really the making of molecules, reach out, and I will be more than happy to have your personal experience of making a molecule on this technology. The two parts that I want, that are somehow closing this presentation, and then we can leave it open to questions, are actually the two components, the two hardware components. So irrespective of the cloud, which is living in the cloud, and of the entire software stack orchestrated by OpenShift, we have, of course, hardware components that are very important. So as I mentioned before, the chemical hardware that in this specific case was a flex autoplant. And then we have also instrumentation for running analytics. So this is what I forgot to add in the recipe, but I can show you one example that I was running yesterday on actually on the same molecule, to give you exactly the perception of what is going to be generated after the synthesis. A little bit more in detail, the flex autoplant and the configuration that we have at the moment is actually capable of handling liquids. We have a stack of 6 reactors. The 6 reactors can actually work in a synchronous way, which means we introduced a certain level of parallelism, and that actually allows you to use really 6 reactors for 6 different reactions, or for allocating the 6 reactors for a large multi-step synthesis. We have also the possibility to handling solid. Again, for the interest of time today, I did not have any solid handling, but we are using a concept that has been developed by Chemspeed, and it's very effective in handling also air-sensitive or moisture-sensitive solids. So the idea is to encapsulate the solid in very thin glass vials, and then use these glass vials like carriers that we drop into the reactor, and this can be imploded at specific pressures in order to release the reactants in the reaction medium whenever is needed and at whatever time of the execution of the synthesis. The last part is relatively standard, but still highly connected and integrated with the hardware from Chemspeed, is an high resolution time of flight mass spectrometry. So we rely extensively on the mass spectrometry with the intention to add in the next months also an NMR capability for augmenting the analytics of the reaction mixture. I want to leave you here with a few links. There is the making of RoboRxN on YouTube. If you have time, have a look for the long version. If you have short time, there is a short version, the blog. And if you want to get more information, please refer to RxN and then / RoboRxN. I want to close it here, and while I'm sure Chris is putting together, collecting the questions, I will also switch the view and see what is happening so that everybody can see what is happening basically in the entire synthesis. Exactly. Chris.
Thank you, Theo. Very interesting presentation, and I repeat myself, one of my favorite projects that I encountered here at Chemspeed, not least because of its visionary quality. And I truly believe that this technology can change the way we will do chemistry in the future. I see there's quite a few questions that we have, but before we go into them, out of personal interest, let me ask you why you chose chemistry for your research, because the way I understand, you're specialized in artificial intelligence and machine learning. And that's a topic that can come with many different applications. I mean, you must have lived under a stone during the last years if you haven't noticed some of the news that come out of this branch of research, and the possibilities basically seem endless. So why did you choose chemistry? And what I'm trying to get at here is basically the question whether this is one of these 2008 moments when the iPhone hit the market, basically for reasons of the supply chain, where all the components that were necessary to build a system like that would allow it to do so. So what do you think what is the main reason that a machine like that was built at this point in time?
Mm-hmm. Again, first of all, why did we choose chemistry? It's a sort of also personal question. I myself, I'm a chemist, theoretical chemist, but every time I was, and even if I decided to go for a theoretical study, I was always extremely fascinated by the complexity of the chemistry behind organic synthesis, and the advent and the possibility to use advanced machine learning algorithms, also coupled with the increased computational power and the possibility to collect more and more larger and larger data set, basically triggered in me the question, can we build a system that instead of driving a car, you were making the example of autonomous driving, can actually help as an assistant in those laboratory tasks that are tedious and that are taking quite a lot of time. For everybody in this call that is doing lab work, I mean, I think they know exactly the amount of time that takes to go through even a simple procedure like the one that we have been sketched here for this webinar. So the idea was really, let's push the boundary and let's see how much we can learn out of the big amount of data that we have in the chemistry world. And this is more or less the underlying, the scientific motivation. Then, of course, there is also an important concept, which, in my opinion, is in line with what we see in the society today. This concept is doing nothing more than providing a different way for chemists to work even in difficult conditions. So this means you can access a laboratory with the support of machine learning model and automation remotely. You can do your experiments while not being in the lab and spend more time to actually in those creative steps that are way more significant for all of us humans. So it's really the introduction of, or rather the introduction, they confirm that a different way of working, even in an environment, even in a field that is very traditional, like the one of synthetic chemistry, it's actually possible when you integrate technologies and when you take advantage of this big data revolution.
Thank you for this explanation, Theo. In the interest of time, I still want to answer two questions because we have very good questions. So we're going to be 5 minutes late. Can we have the first questions, please? Okay, so the question is a specific one about chemistry. So can you apply a system for polymers? Theo, do you want to take this?
Mm-hmm. Absolutely. In the meantime, we also recovered the link. At the moment, we just stopped the entire edition of the cyanogen bromide. We were a little bit late, so apologize. But I will give you still an overview of how it looks like the synthesis, maybe in the next minutes. So you can apply to polymers, definitely the entire concept, the entire stack. We have projects that are exactly trying to imitate what we do for chemistry, for polymer chemistry. The only difficulty is, of course, I mean, the first one is in the data representation that we are working on. So polymer are different than molecules, so we couldn't really use the text representation. We had to revert to a different type of representation for training the models. And the other difficulty that we are working on at the moment is the one of collecting a large and sufficient number of data points for teaching a system what happens when you want to combine different building blocks to make, I don't know, copolymers or anything like that. So it's actually possible. We are internally starting to work on the software asset. From an hardware perspective, you have, of course, a slightly different complexity. But I leave it to you, Christian. I'm pretty much sure that some of this hardware can be adapted also for polymer chemistry.
It definitely can, and we will be in touch with the person who asked the question. Second question and the last one, can the AI be connected with kinetic model or DFT model for obtaining molecular information?
Yes, this is also a very interesting part. This activity, I need to just give a few minutes of introduction. This activity is part of Future of Computing, where we believe that the combination of different approaches, including simulation, is actually accelerating the entire discovery cycle. So with all the limitation that you can have with DFT or any other type of modeling scheme, we still believe that there is lots of value, especially when you start combining DFT calculations with correction kernel based on data, like machine learning. This can give you actually results that are very accurate, even for molecule in solution. So it's, of course, something that is interesting for many people. It will be, for sure, one of the topics where we will try to explore more in the future.
Excellent. Thank you very much, Theo. We are running out of time, unfortunately. Once again, Theo, thank you very much for joining us today and for your time. To the audience, if you are interested in this technology and if you want to further its development together with us, please feel free to reach out to us. We'll be happy to answer any questions you have, and we'll get back to you by email in regards of everything that you typed into our Q&A window today. So this was the first webinar in our series about the digitalization in R&D and QC labs. Our next event will be dedicated to how automation enables a more intuitive approach to R&D. And for more information about this, please have a look at our homepage. Thank you all for your attendance, and we see you in the next one.